Okay, so the goal for today's lecture is to define, so today's goal is to define for a p-adic formal scheme. The sheared prismatization so this will be a functor from p-nilpotent rings to groups. So the starting point, is that so in
so are you so you're saying that for fixed x this thing will be such a function?
Yes. Okay, so a week ago we discussed okay, so let's recall from last time. So let me now assume that x over smooth CP is smooth. So in the previous lecture, if you have a smooth p-adic formal scheme, we discussed the shear de Rham stack. So this was a functor of the above form, and it had the key property that quasi-co of the shear de Rham stack is exactly the p-complete derived category of D modulus. As p-complete. An example, an example is the case of A1. So the shear de Rham stack of A1 is given by the quotient of GA by this object GA chart, the divided power completion, the completion with respect to the grading of the divided power neighborhood of the origin inside G. So the goal is to give a description. So this is as in the theory of prismatization. The goal is to give a description of the de Rham stack, of the shear de Rham stack in terms of Witt vectors, and this description will allow for sort of various an extension to the prismatization. So the first goal is a Witt vector description of X shear de Rham, but in particular of A1 shear. Okay, so right. So maybe one thing I should say is that this presentation of shear prismatization is that I wanted to describe today is not the original one that we considered. It's one that was suggested by Grunfeld actually a few weeks ago, and so I think it's a much clearer approach than the approach we had in mind. So okay. All right, so this approach is based on a construction denoted W check. So the next thing I want to explain is the sheaf of rings W check. So
maybe just one remark. In fact, the same W check is also considered in the ongoing work by Ike Lau, except that he considers this not a sheaf of, at least openly he says he considers not as a sheaf of rings, but also he considers its values on a certain class of rings. But in fact, and the notation is borrowed from his work.
Yes, thank you. So my goal is to explain. My first goal is to explain the construction of the definition of W check, But to start with, I need to recall some constructions from last time, some definitions from last time. So the first definition is that, okay, so if R is any ring, we have an ideal W hat of R sitting inside W bar is the ideal of bit vectors such that all x of I are nilpotent. And x of I equals 0 for I sufficient. So this is an ideal inside the ring of bit vectors. It's an ideal stable under delta. Okay, and Q, the functor Q, denotes the sheafification of W mod W. So W mod W hat is, well, we consider this as a pre-sheaf of delta rings on all p-nilpotent rings with respect to the flat topology, and we take its sheafification. Okay. And in particular, so a useful fact. So to felt is that if the reduction of R is semi-normal, then Q of R is W of R on W hat. So a priori, the construction of Q involves a sheafification, but in fact, one does not need to. Right? So one does not need to if you have the semi-normality condition. Okay. Okay. So there's a couple of basic constructions on Q. So Q, we still have the Frobenius. So the Frobenius from W to W. And an object that I'll call B hat from W to W, that called B hat from W to W. So B hat is the same thing as V if P is greater than 2, and if P equals 2, B hat is B hat of X is B of brackets minus 1. So this has the feature F B hat equals B hat F equals P. So in particular on I'm sorry, on Q I should write, so sorry. Okay, so I should write Q. And furthermore, so maybe this was at the end of last Monday's lecture, is that well, you have an exact sequence. 0 maps to Q via B hat. It maps to Q, and the co-kernel is GA bar. The co-kernel of that in sheaves is this object called GA bar. So here, GA bar is a functor which sends R to the colimit perfection of R mod. So it's a colimit of Frobenius on GA of okay. So so now let me explain the definition. So the definition is, so W check is going to be a sheaf of delta rings on all p-nilpotent rings, and W check is defined as the fiber product of W over Q with Q perf. So here, Q perf denotes the inverse limit under F of Q. So recall, so W is equipped with a Frobenius, which with the map F, which comes from a delta structure, and F descends to Q, and Q perf denotes the inverse limit along F of Q. So in particular, note that Q perf is a delta ring. Such that Frobenius from Q perf to itself is an isomorphism. So the idea of W check is that we're starting with a neutral ring of bit vectors, and we're sort of performing this modification when we form, well, we first quotient W by this ideal W hat, sort of small bit vectors, and now this is a delta ring. This is still a delta ring. It's a delta ring on which the Frobenius is definitely not an isomorphism, and we sort of modify it by forming this fiber product. Okay. So let me just make a couple of remarks about this Q-perf construction. So a remark is that because Q-perf is a delta ring such that Frobenius is an isomorphism, it follows that Q-perf is p-toroidal free. So a remark is that Q-perf is p-toroidal free. But in general, it's not p-complete. And the reason is that Q is not p. So the basic idea, basic principle, is that all of these constructions of sheared prismatization are to W check as usual prismatization is to W. So sheared prismatization is this object W check as usual prismatization. So in particular, a lot of constructions that one does with the bit vectors, one should carry out analogous constructions. So when there are these various constructions with bit vectors that gives rise to prismatization, one should carry out analogs of these constructions with W check replacing W to get sort of shared analogs. So this was the idea that I wanted to say something about today. And in particular, I wanted to say something, a few more things about this construction W check. So maybe I should say, right, so this definition is student infeld and okay. So let's see. So let me explain some structures on W check, and let me give some examples of them. So okay, so first of all, well, we said that we have the Frobenius on W, and so that commutes with everything, all of these procedures. So it gives you something on W check. Also, V hat, this operator V hat. Okay, so I guess we should define V hat using this formula on W, and then it gives an operation on Q, and because V hat commutes with F on Q, it gives you an operation on Q perf, and so on W check. So the structures, so basic structures on W check. Well, first is that you have the map Frobenius from W check to W check. You have V hat W check to W check. So these are, to think of W check as a fiber product, these act individually on the terms of the fiber product. So the next thing to say is that so W check is defined via this fiber product, but both of these maps are surjective in the flat topology. So note that both of these maps in question are surjective in the flat topology because everything, W maps to Q is surjective, and also the Frobenius is locally surjective on Q because it's locally surjective on W. So first is we have these operations. And second, because these maps are surjective, we have short exact sequences of sheaves. We have short exact sequences of sheaves. So, so the first thing to say is that, so if we look at this map is a surjection. The map from W to Q is a surjection, and the kernel is W hat. So when you pull that back, you get a short exact sequence. 0 maps to W hat, maps to W check, maps to Q. Right. So what does it mean to give an element of W check? You give a bit vector together with a compatible system of Frobenius roots in Q, and if you have a bit vector which is already in W hat, then you just take 0 as your system of Frobenius roots. So, so you get such a short exact sequence of sheaves. Okay, but we can also use the other sequence. So, so Q perf is mapping to Q surjectively, and the kernel is the Tate module of Frobenius on Q. So we also have a short exact sequence. So W check also maps to W, and the kernel of that is the Tate module of the Frobenius on Q. So we have these short exact sequences. Okay. So so let me make a couple of comments. So one remark. So I think these sequences give some control of the construction Q. Maybe the first thing is these are short exact sequences of sheaves. So if you evaluate them on an individual ring, they might not remain short exact. But so a remark from this is that suppose R is such that R reduced is semi-normal. So suppose R reduced is semi-normal. So then there's no W hat closure. So H1 of W hat is 0. So that means you get actually a short exact sequence on individual terms. So this means that you get a short exact sequence. 0 maps to W hat of R, maps to W check of R, maps to Q perf of R. And also Q perf of R is the inverse limit of Q. And again, Q is maybe not totally explicit on all rings, but in this case, this is the inverse limit along Frobenius of W of R on W. Okay. So that was one thing I wanted to explain. So another comment. So another way in which this is useful, so this was by Claudia, is that Q perf has, so in particular, I want to describe what this W check does, say, for the p-adic integers. So another key feature is that, so if you have a nilpotent ideal, then so then Q perf of R is Q perf of R mod I. So that's going to be because some power of the Frobenius is going to annihilate the Witt vectors of this ideal. So the difference okay, so if you have no potent ideal, this
and probably you have the same story for W perf. You can do maybe we don't need it now, but in principle you can do the same construction with W. There is also this similar.
Thanks. Yeah. So right. So in fact, this is true already at the level of W. So this is because the Frobenius is nilpotent on the Witt vectors of the ideal I.
Yes, and also it's important that I is nilpotent, not merely each element.
Yes. It's nilpotent answer. Okay. So a consequence of this. So an example is that we can describe W. Yes.
I'm just going to check. The test category is still P nilpotent rings.
Yes, so this test category is P nilpotent rings, but we will extend it to something like ZP or a P complete ring by taking the inverse limit mod P to the n. Okay, so right, so the example is for instance, we can use this to describe W check of ZP. So we can use this to describe W check of ZP because we can use this short exact sequence. So this short exact sequence, well, W check of ZP is really the inverse limit of W check of Z mod P to the n. So so if we look at this short exact sequence, and if we take R to be Z mod P to the n, well, by this remark, Q perf of Z mod P to the n is the same as Q perf of FP. And for FP, for perfect rings, all of these are just the Witt vectors. So for perfect, so all of these constructions reduce to the usual Witt vectors for a perfect ring. And so what we get is a short exact sequence where you have 0 mapping to W of ZP, mapping to W check of ZP. And this maps to now W of F. 0 CP, and this is also Q upper perf. So the conclusion is that W check of ZP in this case is a subring of W of ZP. And it's exactly the subring given by ZP together with the sum of ZP together with those Witt vectors whose Witt coordinates converge to 0 p-adiply. So let me make a couple of other comments. So I want to use now the second sequence. So another one. So W check is defined using constructions which are not P complete, namely Q and Q perf. These are not P complete rings, but the remark is that W check of R is always P complete. Always complete. And right, so I think this is going to follow from the second exact sequence. And the reason is that, well, it maps to W. I need to be a little bit careful here. Well, sorry, I guess what I mean is that is it is an inverse limit of things which are sort of isogenous to W.
Be complete means in the naive sense or derived. So W hat is the usual ring, but for in particular, it's a usual abelian group. Now, what do we mean? Yes, so there is a naive notion of P completeness, and there is a notion of derived P completeness for complexes, but in particular for a abelian group. And something to keep in mind is that usual P completeness implies derived P completeness, but not the other way. And a typical example when you have derived P completeness, but not usual one is what you take, for instance, a completed direct sum of countable many copies of CP. And then you consider an operator from this group to itself. Well, for instance, just consider the operator which multiplies the ith coordinate by p to the I. And then what we see is that the image of this operator, in this particular operator, is injective, but the image is not closed. Am I right? It's not closed. So if you consider the quotient, it will be not and equipped with a topology, it will be, and with the natural topology, it will be not separated. And therefore, and here when we say P complete without the word derived, this means complete and separate. And so, however, this quotient is derived P complete. Yes. And this I'm trying to repeat your lessons. You explained it a few years ago in a second.
Okay, yeah, thanks. So I think maybe to be safe, I should say derived P complete. I was hoping that's not necessary actually, but okay, so let's do that. Okay, so maybe let me make one.
So sorry.
Yes.
How to C3?
How to C3? Well, I think it's so right. So you have a short exact sequence of sheets.
So you are using which exact sequence here?
This short exact sequence of sheets, and this is P complete, and this is P complete, and I think that means that the global sections will be derived P complete. Global sections on anything.
And TF is what? Is kind of mock Tate. It's a Tate model, but defined. The usual Tate model is defined using multiplication by P. So you take the kernels of P to the power of n and then form the inverse limit instead of the use. And here you do the same thing with F playing the role of this is continuous. So it is F complete, but our situation is the same as.
The kernel of Frobenius on Q is skewed by B, right? So it's multiply P complete.
That's right.
Therefore, the inverse limit.
Yeah. So this is the Tate module of F on Q, but anything which is in the kernel of F is also in the kernel of P. So this is an inverse limit of groups which are each of which is annihilated by some power of P. So
just one more thing. So when you are saying that a sheaf is, let's say, derived P complete, is it a condition for pre-sheaves, in fact?
Yes.
Yes. And in some, so it's in some sense the notion of derived completeness is in some sense simpler than the usual completeness, because for usual completeness, it's saying that something is an inverse limit, it's quotient and low power that P. Then if you deal with sheaves, then you have to ask yourselves whether you consider quotient in the sense of sheaves or in the sense of pre-sheaves. But the notion of derived P completion has a different flavor. It's if you unravel the definition, it means it has the following. So we have a let's say an abelian group A, and then you just form a certain product of countably many copies of A, and then consider certain endomorphism of this product defined by an explicit matrix. And then derived P completion is a requirement that this map is an isomorphism. Yes. And because here only products appear, products of sheaf is the same as a product in the sense of pre-sheaf. And so when you consider derived P completion, it doesn't matter as far as I understand whether you work with sheaves or pre-sheaves.
Thank you. Okay, so yeah, so it will always take values in derived P complete rings. So I think I would be, well, I would be interested in trying to understand this ring, but more generally, so I want to make a couple of more comments. So right, okay, so the statement is so 4 is that so W check always maps to W, and that map is locally surjective in the flat topology, but perhaps it's hard to say, right? It's hard to say how far. It's not pointwise surjective.
Just so when you say locally surjective, means surjective as sheaves.
Yes.
And when you say pointwise surjective, this means surjective in the sense of pre-sheaf.
Yes. So W check W. Well, we said we have an exact sequence of sheaves, so this is surjective as sheaves. But on the other hand, it's very much not as pre-sheaves. But so right. So in fact, there's a couple of remarks that I wanted to make about this. So maybe the first remark, which is always true, is that the kernel of this map is a square zero ideal. So the kernel of the map from W check to W squares to zero. Well, I should say is a square zero ideal. And the reason for this is what is something which is in the kernel of W of W check to W. So it's an element of this fiber product, but it's zero in this component, which means it's zero here. So it's an element of Q perf, which maps to zero in Q. And so the fact that it's a square zero ideal follows from the following statement: given any two x and y in Q, such that x and y are P power quotient, or F power quotient, we have x, y equals 0. This was a lemma that I mentioned in the previous lecture. So it's a square zero, it's always a square zero. The kernel always squares to 0. And in fact, I think the kernel is often 0. So if R is a ring such that, let's see, so if the nil radical of R is nilpotent. Then, well, in fact, W check of R maps injectively into W. So, right. So maybe there's multiple ways of seeing this, but I think one way to see this is right. So again, what does it mean to be in the kernel? Well, we need to show that given an element X in Q of R.
Just so W check, but I think you also said that it maps such.
Sorry, this is a point.
Point-wise.
Yes. Okay, so and the reason is that okay, so what does it mean for something to be in the kernel? Well, it means you have to have something in the f-adic tape module. And so the observation is that if you have something X in Q of R such that X is p power torsion, there exists a uniform power of f. And this uniform power of f is going to be a function of the nilpotence of this ideal, such that f to the n of x equals 0. So in particular, that's going to mean that this f-adic tape module will vanish. So I think maybe this is related to the comment, the observation over here. Okay. Right. So these are a few general comments. So in particular, this means that
Just so where did we use that the nil radical is nilpotent? Because the word uniform relies on this.
So the reason for this is okay. So
Maybe I have a request. Just speak a little bit slower.
sure.
Just because otherwise everything is very clear, but because the speed is a little bit too high, it's a little bit hard to follow.
Okay, so maybe let me explain this point because at least this is something I would also like to understand better. And so, okay, so let's prove this. So prove. So what I want. So let's consider. So let's consider an element X in Q of R, which is p power 4. So let me represent it. So let's represent it by a bit vector. Sum of b to the I is y. Well, then the claim is that it's p power torsion if and only if you have an element of Q of R, then well, I'm sorry, maybe let me say it this way. So suppose we give an element X in Q of R, which is represented by a bit vector like this. Then X is p power torsion in Q. If and only if there's a uniform nilpotence bound on all the X phi. There's a uniform, I should say, in I. But okay, so in this particular example, we're considering a ring in which okay, so maybe I should say there's a uniform nilpotence bound, and in this case, the order of torsion, I should say that the order of torsion, I should say there's a uniform nilpotence bound on the x sub I, there's a uniform nilpotence bound, let's call it m, and then there exists n, which is a function of m, such that f to the n times x equals 0. So the order of p power torsion, or the order, or equivalently, the order, the exponent of Frobenius that kills an element of Q is a function of the nilpotence bounds on the given bit components. And if you're in a setting where the nil radical is actually nilpotent, then that will mean that there's a uniform bound on the p power torsion in Q. Okay, so, and that in turn will mean that you cannot have.
So again, how do we use nilpotence of the nil radical? At the very end.
So we're using it at the very end because we're saying if we have an element which is p power torsion in Q, there's a uniform nilpotence bound on all the bit components, and that in turn means that there's a uniform power of Frobenius which annihilates that element. So that means that the Tate module must be 0.
Because the first it was uniform in I, but nilpotence was the degree of nilpotence may depend on I.
Yes.
And now, because the nil radical is nilpotent, it's uniform not only in I, but also it's just uniform.
So maybe one can also argue this fact. Right. So maybe one can also argue this fact directly using item 2 over here.
Item 2 means that Q-perf doesn't feel simplified.
Okay, so let me explain. So in particular, what this means is that if you have a polynomial ring, so in particular, if you have, maybe this example is kind of important. If R is something like a p-complete polynomial ring, in infinitely many variables, then W check of R is some subring of W of R. Okay, so we said that if R is ZP itself, or some variant of ZP, then we could say exactly what W check of R is as a subring of WR. And the question is, what is the subring?
And do you have an answer to this?
No, wait. Well, we have only been thinking, we only learned about this a couple of weeks ago, so haven't. This is a question.
It's a question to us. Or is it a rhetoric question or a non-rhetoric?
It's a question that we would like to know the answer, and hopefully we'll also think about. But
okay, so it's a question. It's an exercise for us, and
for us,
yes.
Yes. Okay. Okay. So I wanted to explain. All right. Yes.
For 4B here,
Yes.
are W check and W dash after sheafification?
I'm sorry.
Are W check and W after sheafification?
I mean, this is W check evaluated on a given ring.
And that means I see. So that means just W check the function we defined earlier, not like W check sheafified on the FP.
I mean, W check is a sheaf. I'm sorry, but we're saying the W check maps to W.
Oh,
that
yes, my
maps
bad.
to
I see. My bad.
That's useful. Okay. Okay, so let me explain. All right. So now I want to connect W check to the sheared de Rham stack, And so this comes from the following facts. Okay, so the first statement is that so W check has a Frobenius, and the statement is that Frobenius from W check to W check is surjective. So just as Frobenius on the vectors is surjective. So again, this is as sheaves. Okay, and two is that you can identify the kernel of Frobenius is naturally identified with this group M scheme that we encountered earlier, GA short. Is that all I wanted to say? There we go. All right, so okay, so I think this is going to follow. So the proof is, well, basically, we look at this short exact sequence, and on this short exact sequence, Frobenius is an isomorphism here, and well, it's also locally surjective on W hat, and the kernel on W hat is exactly GA sharp hat. Position. Position is that Frobenius on W hat, the W hat is locally surjective. So this does require a little argument. And the kernel of Frobenius is identified, the kernel of Frobenius on W hat is GA. So this is an analog for W hat of the statement about bit vectors. The bit vector Frobenius is locally surjective, and the kernel is GA sharp, sort of the hat version. As far as I know, the version for the bit vectors of this local surjectivity does not seem to formally imply the surjectivity on W hat. So as far as I know, it's a different. All right. Okay, so another remark is that we have the hat from W check to W check, and this is injective. And the co-kernel, again, as sheaves, is just, that's because, that's because W check, that's because we know the analogous statement on each of the terms. So that's because, check, simple back W over Q. Over here, we know that V is injective in all of these terms. Co-kernel of V is GA, over here it's GA bar, over here it's
Instrumentation V check or V hat? I don't know.
Thank you. Okay, so right. The basic starting point. Basic construction. So we consider W check derived mod P as a functor from P no rings to spaces. Well, to group points, I guess.
So you consider the derived quotient by P?
Yes, as a functor from P-nilpotent rings to group points. So one comment is that we're really doing this in sheaves. So remark is that we're forming this in sheaves of points. Which means that at least a priori we're not doing this construction pointwise. Though I think in reasonable settings, it will just be the pointwise construction. Okay, so the proposition is, okay, so if P is greater than 2, then there's a natural isomorphism between W check mod P and the shear de Rham stack. So A1 mod P so statement. Right, so if P is equal to 2, one can give a modification of this where instead of right, so instead of P, one takes FV V hat of 1. So P if F V hat of 1. The statement at all. So
Did you say that the first one is as rings?
I'm sorry?
Is it as rings or is it?
Yes, it's going to be as rings. It's going to be okay. So right. So really, this is taking values in one trunk. Okay. So this is taking values in one truncated animated rings. As is this. So this is okay. So sheaves of one truncated animated rings. Okay. So this is an analog, right? So this is sorry. So this is an analog of W derived mod P is A1 Okay, so let me, and in fact, it's proved more or less the same way. So proved. So okay. So if you have cone of P on W check, so you want to relate the mapping cone of P on W check to the mapping cone of GA, well, the mapping cone of GA sharp hat to GA. And well, we can define it. So right, so how do we define these objects? These objects are defined as one truncated. These objects are sort of specified via DGAs. We have one truncated CDGAs, and there's a zigzag of maps of CDGAs. So we have this map multiplication by P. So I mean, this is the same as what one does in so this is basically following the argument, testing argument. Okay, so let me assume P is greater than 2. So we have the Frobenius. So on the one hand, we have the mapping cone of P on W check, but we can give another. So in general, whenever you have such a DG algebra, we can form a quasi-isomorphic DG algebra by just forming the pullback. So by taking the surjection of sheaves and forming the pullback. So here we have x comma y and W check such that f of x equals P times y. And then we can give a map from here to GA. So map here to GA, which is sending a bit vector, an element in W check. We just remember the underlying bit vector and well, remember the zeroth goes component. And this map is going to send x comma y to x minus so x minus v of y will be an element of W check such that Frobenius is 0. So that's an element of So this is exactly the same as the proof in the shared setting. So you write down a zigzag of quasi-isomorphisms of UGAs. So okay. So let me make one more comment, and then maybe we should take a break. So one more comment. Yeah, so one more comment. Right, so as I mentioned, so in particular, this means that, so the shear de Rham stack is equivalent to this construction W check mod P. So it would be good to understand what W check mod P looks like as a sheaf of, one truncated animated rings. Well, so I mentioned some things about W check, and in general, you have a map. So for any R, you have a map from W check of R, right on P, to W check on P. So this is really the construction one wants to consider. A priori, this map, well, it involves some sheafification. So a priori, there's an obstruction to lifting a class here to a class here. So a priori, is an obstruction class. So again, this map is fully faithful. There's an obstruction class in H1 W check, P torsion obstruction class, to lifting to W check of R, right. However, we use the short exact sequence. So we have a short exact sequence. W check maps to Q perf. And this receives a map from W hat. So here, Q perf has the property that its derived P completion is vid vectors of G of R. So that's not going to have H1 classes. So if you have a torsion cohomology class here, gives you a torsion cohomology class here, but this doesn't have but the torsion cohomology classes here are the same as in the P completion. Yeah, so I think there's no cohomology. There's no cohomology in these conditions. There's no cohomology here. So this will tell you that it's actually an equivalence here.
For any R.
Yeah, that's right. If there's no H1 of W check classes.
Sorry, but then
I think so.
So again, the claim is that this is an equivalence for any R if or for any R satisfying some condition. Yes. Or which condition?
That the semi-normality of R reduced.
Mm-hmm.
Maybe now's a good time to take a break.
can you just explain again why obstruction class vanishes?
So I think the obstruction class is say the obstruction class is in here and it's P torsion. So it gives a P torsion class here. But okay, so let's try to do this carefully. Let's check that we didn't make a mistake. So you have a class in, okay, so you have a class in H1, QPerf, which is p torsion, and this will map to a class in H1 of W of GA bar. So I think if you have a, so let me make sure I'm saying this right. Oh. You have a, I think if you have a torsion class here, it'll give you, right, so there's a map from Q upper perf W of GA bar. It's an isomorphism on P completion. So I think if you get a torsion class here, that will have to go to a non-zero torsion class there. And right, and I think this is going to be 0.
So you're saying that H1 P torsion class in H1 of any shape of rings is the same as P torsion in H1 of its P completion.
So yeah.
And P completion of QPerf is very simple. This is W of a perfect ring. Right, so
Maybe can we take a short break here?
Sure.
Okay, I'm unable to follow.
but maybe, yeah.
Okay, yeah, so I apologize. I was doing some nonsense here. So let me rephrase this as a question. So question, when is right, so you have a map from W. Rephrase this as another question. Question, you have a map from W check of R mod P to W check mod P of R, and when is this map going to close? So that's a question. Okay. So I thought maybe in the second half of the talk I would actually try to define this sheared prismatization and say a little bit about it. So okay, so I want to define
so maybe you already explained. But if R is ZP,
yes.
You prove that this is
We proved, okay, so we actually proved for ZP. So I thought for ZP we only described the side.
this logic describes a quotient.
So maybe is it okay if I
Sure.
I mean, yeah,
Yeah.
maybe we can come back to this point. Sorry. Okay, so I just wanted to actually define ZP sheared prismatization and sheared prismatization. So right, so again, the idea was that one can take the definition of prismatization and replace W by W check. So in particular, define ZP sheared prism. So ZP sheared prism. So okay, so let's first say it this way. So given an element C in W check of R, have the notion of it being primitive. So we'll say that C is primitive. So C maps to something in Q of R, and it maps to P times the unit in Q of R. So alternatively, C maps to, well, so it's a notion of a primitive bit vector. So, okay, so sorry. So I guess I should say that this is if and only if C maps to an element of W of R, which is primitive. So being primitive in W of R means that the first bit component is nilpotent and the second bit component is a unit. So that means that when you map to any perfect field, you get P times. Okay, so we have the notion of a primitive element of W check of R. And well, the collection of units in W check of R acts on the collection of primitive vectors. So we define ZP shared prism as the quotient of W check prim by W check plus. So this is analogous to the definition of ZP prism, where you take primitive bit vectors, mod units, and the okay.
I really remember that in Vadim's talk in October, at that time there was no W check, and the definition was different.
Okay.
Will you prove that they are equivalent? Or?
Yes, yeah. Right. Sorry. So again, so as in the specification, we want to deform P, and so the idea is that you replace it by a primitive bit vector. So this gives the definition of ZP Sheared prism. Okay, so maybe I should also say that there's a prismatization of A1. So similarly, well, in general, we define, so X is a together from the scheme. Then we define X sheared prism to be the vector from kenopotent rings to groupoids on an X sheared prism of R. Well, first you give a point of ZP sheared prism of R. And you give a point of X applied to W mod C. So over ZP sheared prism, we have a ring stack. Given by W check points. Okay, so this is, I mean, this is parallel to following the definition of.
So, for instance, if X is A1, if X is the affine line, then you just have to first choose C and then the point of the derived quotient of W check by C. Yes, and just as in the theory of usual, not shared prismatization, in general, this is a derived stack.
Yes.
So, and so there is some. Until now, we didn't need mated rings. The only animated rings we worked with were sort of the short animated rings in degrees 0 and -1. But my understanding, so is here R is an important. Just what is R here?
Oh, okay, I was just considering classical rings for now.
The classical rings, and so you will not, and therefore you don't feel that X.
Well, I only defined all these, we only defined Q and so forth right now for classical rings.
Yes, and therefore your X sheared prism is a stack on classical pinned rings, which is not really enough.
Which is, yes.
But for a large class of schemes X, this is enough. So in general, this is at least a good approximation.
Okay, yeah, so in particular, right, I wanted to start by assuming X is smooth over ZP. Okay. Okay, so I just wanted to start by so there were different descriptions of ZP sheared prism, and so Vadim explained in September or in the fall a different description, and I wanted to explain sort of how to connect. Okay. Right, and so maybe we should just remark. So in particular, note that for p greater than 2, we have a natural map from the spoke of ZP to ZP sheared prism. Well, maybe I should say for any p. For any p, you have a map like this, and can pull back.
Just so what is this?
Sorry, this is classifying p. Which is primitive in W check. And so you can
Classifying p means what does it mean classifying p?
Well, right, so we need to give an element of so it's given by the element p in W check of ZP.
P of C classifying.
So I mean that this is right. So a map to from
What is the meaning of the word classifying here?
Okay, I just mean defined by. So it's defined by this element of W check of ZP. So you can pull back X sheared prism, which lives over ZP sheared prism, along this map. Okay, so for p greater than 2, this is exactly the sheared Durham stack. So I don't know, maybe this should be called the crystalline point. So for p greater than 2, this gives this pullback is exactly the sheared Durham stack. For p equals 2, it's something slightly different. So in particular, for p greater than 2, quasi-co of this is a category of p-complete D modules on X. And for p equals to 2, it's something slightly different. And the reason is that this pullback, well, it only depends on the special fiber. So this factors through it's an isomorphism with spec FP sheared prism. So this pullback construction only depends, this pullback of X sheared prism to suppose CP, it only depends on the special fiber. And I think as Vadim explained in the fall, the category of D modules when p equals 2 is not a functor of the special fiber. Okay, so you get some slightly different.
So a general feature of the theory of sheared prismatization is that at first sight, on the one hand, the case p equals 2 is somewhat different. On the other hand, from a higher perspective, the theory is uniform. So, for instance, here in the usual prismatization story, we have for all p X Durham depends only on the deduction of X modulo p. And for here, this is true for the sheared prismatization, this is true if P is greater than 2. And otherwise, you have to distinguish the, so to say, the de Rham point from the crystalline.
So there's also a different de Rham point from both ZP into here, which such that the pullback along that map is a shear de Rham stack, and that point would be exactly this F we had on that.
So this F, this element F V hat of 1 is, so to say, the fake P. And which is if P equals 2, then it's different from the true. Well, for my story, for the problem I'm working on, it's okay. Anyway, that the interesting thing is that for P equals 2, it's fine.
Okay, so
but I would say that this is but this is a feature, not a bug.
okay, okay. So let me explain the following proposition, which will So proposition is that there's the following description of a ZP sheared prism. So ZP sheared prism can be described as the quotient of an in scheme by a group in scheme. So one feature of W check is that it's not really an in scheme; it's some sort of quotient. But ZP sheared prism is the quotient of P plus W hat by 1 plus W hat via multiply. So it's a quotient of this in scheme by this group in scheme. So I think this was the definition that was explained by Vadim. Okay, so the proof, so over here, we have this primitive elements in W check on W check cross. The idea is that consider elements of W check such that, well, W check maps to Q perf, but let's consider elements that actually, well, an element is primitive if it maps to P times a unit. Let's consider elements that just map to P. So consider elements of W check such that they map to P in Q. So, okay, so then the observation is that such elements are exactly. So this means that you have an element such that if you subtract P, it's 0 in Q perf, which means that from one of these exact sequences from earlier, it's in W hat. So it's exactly, this is exactly the set of, all right, so maybe what I mean to say is that the set of elements in W check which map to P and Q perf is exactly P plus W hat. Well, the collection of units that preserve such elements is exactly those units in here, and here we use the fact that Q perf is P torsion free. So we consider those elements of W check that map to P in Q perf, and consider units in W check such that U maps to 1 in Q. And then this is exactly one stuff.
So this gives you a map in one direction.
Yes.
And moreover, yes.
Yeah. So right.
And this, so you get a kind of functor in one direction and maybe a fully faithful functor. But why is it? But you have to. The claim is that this is an equivalence.
Yeah. So it's an equivalence because so if you have an element in W check, so it's an equivalence because if you have a unit in Q perf, you can lift that to a unit in check because the map. So in general, if you have a primitive element in W check, it maps to P times unit in Q perf of R. But then you can lift that unit, at least locally, you can lift that unit to W check and then rescale by that unit to make it exact.
I want to write it down. So can you say it again or write it on the?
Sure. So we have a map from, right, so P plus W check mod one, sorry, P plus W hat mod 1 plus W hat to W check prim mod cross. Well, this is coming from the fact that W hat actually maps into this that plus P plus. Well, we use the fact. So this is fully faithful, and at least locally, it's essentially surjective. Locally in the flat topology, it's essentially surjective, and the reason it's essentially surjective in the flat topology is that given C in W check R is primitive, so then C maps to P times the unit. And then lift the unit.
Okay, so a unit in
W juke.
Q or Q perf, where are we?
Sorry, I keep forgetting.
Q perf. Is it obvious? So by definition, an element of Q can be lifted to a W, locally be lifted to a W. And is it obvious that a unit can locally be lifted to a unit?
I think if you lift the element and the element started as a unit, then
but it's an extension by square zero ideals, so probably.
well, it's not by square
Maybe
zero.
it's even more easy.
I think the statement is that if you have an element, it's an element of Q, it's a unit if and only if when you map to J bar, it maps to a unit. Great. So this statement. And the next thing that I want to do is to explain the different descriptions of the ring stack. So if A1 shear prism, if you have such. So I think earlier, so such an element. So if we think of primitive bit vectors as things that are sort of close to P, these are sort of elements that are extremely close to P, and we're modding out by units which are very close to Y.
So is there in this statement, do you need the unit sign, or should there be like a unit sign later, or?
So I just mean 1 plus W hat under multiplication.
So you don't need like the units in the statement of the proposition?
I mean, any element in 1 plus W hat is automatically a unit.
Oh, okay.
Yeah, so I just mean it's considered on a multiplication.
Oh, I see. Thank you.
So okay, so suppose given, so for simplicity, suppose given an element C in P plus W hat of a ring form. So idea, so this classifies the map. This is classified by the map from spec R into ZP sheared prism. And the idea is that we should produce a ring stack over here, which is some sort of definition of the de Rham stack or sheared rings. Okay, so there are various constructions. So one construction was already mentioned. Okay, so goal is to describe the ring stack. A1, some, but pulled back along C. The ring stack over. Okay, so one description is that it's exactly W check derived mod C. So as was mentioned earlier. But I wanted to mention, so I just wanted to connect this to the description that that Vadim explained in the fall. So another description of this ring stack is the following. So this construction of W check mod C involves Q, and it also involves this inverse limit of Frobenius along Q. But there's a slightly smaller presentation where you just use one Frobenius instead of the whole thing. So one can describe this as a DG algebra I consider W fiber product over Q with Q, where the map from Q to Q is the Frobenius. So it's an element of W together with a root via Frobenius, Q, and we can define a map from W to here. And okay, so we see the idea is that it will send an element X to so it's going to send X to the tuple C of X, and V of X. So we can define a map from W to here, which in coordinates is
just also see there are three. It's a tuple. Is it a triple or a cup? How many?
okay, so it's two elements.
CX twice.
Okay, so it's two elements which are compatible. So maybe I should just so it's CX and V hat of X, and right. So we need to define. So so we can describe the sheared prismatization of A1 in this case as the following DG algebra. So you have W and in degree 1, and you have this ring W fiber product over Q with Q via 1 Frobenius in degree 0, and the map sends an element X to, so it's multiplication by C here, and it's this Verschiebung V hat here. And the observation is that they're both compatible because when you map to Q, well, you get C times X, which is P times X in Q, but on the other hand, you get F times X. So note that this is actually a map to the fiber product. Because C is equal to P in Q. So this is maybe a slightly smaller version of description 1.
Yes. So this ring space, this sheaf of rings W check is a very convenient tool, but this convenience comes at a price because we have to use us to infinite projective limits. And there are more economic descriptions. This is a more economic description.
This is a more economic description. Another thing to say is that in the theory of prismatization, one of the important features of the bit vectors is that for any delta ring R, there's a natural map from R, a natural map of delta rings from R to W of R. And well, this is not clear to me what the analog of that for W check is. But if you, in fact, if you use these other descriptions, which are not so far from the bit vectors, then you can produce an analog of this map, at least up to some power of Frobenius. So maybe one thing that I should explain, or at least I should mention, but so a remark.
I'm sorry, Akhil, can you hear me?
Hi, yes.
I had a question about the previous point, which was you said CX equals PX in Q,
Yes.
but I thought the definition was that C is P times a unit in Q.
So I was assuming, okay, so I was assuming, oh, sorry, you can't see the top board, but I was assuming that C is actually in P plus W hat.
Oh, great. Okay, thank you.
Yes. Okay, so maybe just a remark is that so maybe a remark is that in general there's a map from the usual prismatization to the sheared prismatization, such that when you compose with the map from sheared prismatization to the usual prismatization, it becomes the Frobenius. So this maps, in particular, there's a map from X prism to X sheared prism. Well, there's not really a map from, so maybe it's not so clear how to see that directly on W check. But okay, so in fact, you can see that using some of these other descriptions.
So you are saying that using W check, it's not clear how to. So here you have to produce two maps.
Yes.
Is it hard to produce both of them or one of them?
Well, there's a map from W check to W. So all the constructions involving W check map to all the constructions involving W. So you get this map. But if you add a Frobenius, there's also a map in this direction. And a remark here is that maybe a related remark is that so it's not clear that a remark is that
I want to write it down. So so in the language of W check, one of the map is clear, but the other is not. Which one is not clear?
This map.
Thank you.
Okay. All right. So yeah, so maybe a related fact, if I can just mention it. So a related fact is that, let me just say this for P. So W check mod P derived mod P maps to W derived mod P. And this map is not an isomorphism, but it has a section up to Frobenius. So there's a map, I don't know what to call it, F, such that the composite of F and this map is the Frobenius. So if you go both ways, you get the Frobenius on W.
And this is, and are you saying that F is hard to produce, or?
So yeah, F doesn't, as far as I understand, it doesn't come from a map from W to W check. It's only defined mod P, and possibly mod P to the n. It would be after the n that would be defined.
Is it possible here to, you mentioned at the beginning of your talk that W check is an extension of W by a square zero ideal. Does it help here?
I think it does. I think what will happen is that ideal, the Frobenius, will become divisible. The Frobenius is divisible by P on that ideal. Okay, maybe. Okay, so sorry, maybe I can just say a little bit about this, because also I think this has sort of a nice description, right? So I don't know. So I think this picture is explained by Bhatt. So the idea is that okay, so there are these two descriptions. One is W check mod C, and one is this construction here, and I'll explain a third one, which is going to do this in a moment. So the idea is that okay, so the usual A1 prism over C is the ring stack W to W, component of W to W given by C. And well, you can take a Q version of this. So this maps to the ring stack C. And the idea is that this object right here, well, this is a square zero extension. So as a sheaf of animated rings, it's a square zero extension of GA bar by GA sharp bar shifted by 1. So okay, so recall here that GA bar is right, so it's a colimit perfection of R mod P. And GA sharp bar refers to the quotient of GA sharp by GA sharp. So this fact here is something that I think I mentioned earlier, which is that if you take Q mod P, so C maps to P and Q, so then Q mod P is a square zero extension. So pi 0 of Q mod P is GA bar, and pi 1 of that is the P torsion in Q, which is this sheaf. Okay, so you have the usual prismatization, and it maps to this Q version, which is a square zero extension of GA bar by something. And the idea of shearing is that you get rid of this thing. So you have a natural map, produce a natural map from GA bar into here. And then the shear prismatization is the pullback of the prismatization, the Q version, and this map from GA bar that gets rid of the part here. So now the question is, how do you produce this map? That's maybe the interesting part of this diagram. And one way of producing the map is, so there's two ways of producing this map from GA bar. So really what one has to do is to describe the map from GA bar into here. Because this is not a map of DG algebras. GA bar does not map to Q, it's only a map of animated rings. So how to describe GA bar to Q. So the first description is that it's the map from Q perf mod C, which is also P, to Q. So how do you describe this map as a map of DG algebras and only as a map of animated rings? Well, one description is that you replace Q by Q perf. When you replace by Q perf, that precisely gets rid of pi 1 because Q perf is P torsion free. And description 2 is that you use this Verschiebung. So this is description 1, and description 2, which I'm running out of space. Description 2 is
I didn't understand the first description. Can you say it's so you want to construct a map from GA bar with a cone of Xi.
yes.
This ring group would ring represented by DG algebra is sometimes called the cone. At least I like to call it the cone. Now, can you repeat your first explanation?
So the first description is that you have the cone of Xi on Q that receives a map from the cone of Q perf, the cone of Xi on Q perf.
And then are you saying that the cone on the Q perf is just GA?
It's just GA bar. This is just GA bar because when you form Q perf, that gets rid of all the torsion in Q. So the reason here there's both the pi 0 and pi 1 comes from the P torsion, in Q, which is not there in Q perf. So you have this. Okay. So all right. So but the other way of doing it is well, you just use the Verschiebung. So you have Q mapping to Q via the hat. And this maps via F to Q, and this maps via dinner. So you also have this map of DG algebras. This map of DG algebras is a map from GA bar to, maybe with one Frobenius, to Q mod Xi, the cone of Xi on Q. Okay, so in particular, the idea is that okay, so just write this box. So A1 sheared prism over Xi is supposed to be the fiber product in ring groupoids, stacks of A1 prism with the Q version, so with Q mod C. So the idea is that this is the formula at the level of ring stacks for A1 sheared prism, and these give explicit DG algebras that describe that.
Did you see that these two maps are the same?
I guess that this is going to be the same up to the Frobenius. I mean, okay, so one way of saying it is that it's mapped from a perfect ring. So in general, if you have if you have FP algebras, right? So here's a way of saying it. The idea is that this Q mod Xi, right? So actually, this is somehow the key point. The idea is that Q mod Xi is not only a sheaf of animated rings, it's a sheaf of FP algebras, because you have a witness that P equals 0 here. The idea is that the element 1 maps to exactly P in Q. So it's a sheaf of animated FP algebras. And if you have an animated FP algebra such that pi 0 is perfect, that canonically splits. Because perfect rings have no FP algebras, have no deformations. So the idea is that a shearing, another explanation is that a shearing is exactly, so far this didn't require that Xi was sort of strongly primitive, but the idea is that a shearing is exactly the same thing as making this into a sheaf. A shearing realizes this. Q mod C as an FP algebra. And once it's an FP algebra, that forces the extension to actually split. That forces a canonical splitting into GA bar plus GA bar, GA sharp bar. Okay. Maybe I can explain one more description of this, which
I'm sorry, I'm a little confused. Did you just claim that, okay, so Q is a FP animated, sorry,
Q mod C.
yes, Q mod C is FP animated thingy, I'm okay with that. Did you just claim that it canonically splits?
So once you've chosen the structure as an FP animated ring, it canonically splits. That's because that's a fact about perfect rings, perfect FP algebras, that any square zero extension or any nilpotent thickening will canonically split.
I see, okay, but you do have to pick the FP.
So you have to take the FP algebra structure. So that was the conclusion that a shearing is exactly making this into an FP algebra. Okay, so anyway, so both of these two descriptions are exactly realizing this pullback as sheaves of animated rings. Okay, so maybe the last description is that because it doesn't involve Q and it realizes the shear prismatization as quasi-ideal in the vid vector. So this is what Vadim explained in the fall. So description 3 is that you can, there's a quasi-ideal, so it's,
Do you have a preference which of the two you use?
I mean, I just wanted to describe a couple of different descriptions. Yeah, so I think that's more descriptions as well. Okay, so A1 sheared prism over C can be defined as, again, it can be defined as a DG algebra, but the DG algebra, so it's given by a DG algebra where the zeroth term is just the vid vectors, but I need to tell you what I is, and I is going to be the collection of pairs x comma y and W such that f of x equals c times y and x minus v hat of y is in W hat. So I is, or I sub c is a vector from our algebras to,
and D is projection to
yes, so D is
D of x, y equals x. Something.
D of x, y, thank you. So this is the description, yeah, deep sector. So description 3, so just one comment is that description 3 is actually, well, it's something that you get from description. Yeah, so description 3 is actually a consequence of description 2. So the idea is that in general, if you have any GG algebra, and if you have a surjective map onto the base, then you can from the pullback of the degree 1 part, and that will give you the same GG algebra, quasi-isomorphic GG algebra. So the idea is that you get 3. So you get 3 from 2 by considering the map from W to W cross Q, which sends X to f of X. So sort of pulling back the for vagueness. And then you pull back the ideal, you pull back the quasi-ideal to get this quasi-ideal. Okay, so one thing about description 3 is that maybe it's most concrete because it describes the sheared prismatization as a quotient of a scheme by an in scheme. So it's a quotient of a scheme by an in scheme, okay. So this is quotient. So I think in particular, most of the calculations we actually did to try to work out that sheared prismatization were based on description 3. Okay.
Yes, and when C equals P, then maybe you already mentioned there is a very short, but maybe it was your original definition in the case of the A1 sheared drum is what is cone of the map from GA sharp head to GA. This is also a quotient of a scheme in scheme, but the good news is that in this case you have a scheme finite. Well, here double has infinite.
Yes, but I think as you explained at some point, one can replace this for any given C, one can replace this by Wn for some. So then one can really realize it in terms of refining.
You mean for any C you can replace W by Wn, where N depends on the C.
Yes. So yeah, so maybe one comment here is so yeah, I guess it's almost out of time, but in general, I believe that these stacks, they're quotients, they're always quotients of in schemes by groupoids in schemes, which satisfy some sort of notion of flatness, and so I think that at least well that means that sort of quasi-coherent sheaves on these objects are somehow relatively concrete.
And also, it seems that they have some finiteness problem. Yes. At least if C is B, then you get a quotient schemes of finite type by in scheme, which is sequential inductive limit of finite. That's finite logarithms. And hopefully something like this.
Okay, yeah. So I can say maybe just one thing. So, okay. So there's a few things one can say. So maybe one question in general is describe quasi-cone of X sheared prism in some examples.
You mean that so if X is a fine line, then just a moment. In some examples, so what is the main direction of generalization here? Is the problem to make to pass from C equals P to arbitrary C, or is the problem to pass from X equals A1 to, let's say, any smooth X? So what is
Well, maybe
both?
maybe I should just say one thing. So one is a remark. So remark is that in the prismatic theory, there's an important point of ZP prism, which is the Q de Rham point. So a remark is that there's a natural map. So I'm now going to assume P is greater than 2. There's a natural map from both of ZP double brackets Q minus 1 to ZP sheared prism. So in general, how does one describe quasi-co of ZP sheared prism itself? The comment is that there's a natural map like this from both of ZP double brackets Q minus 1 to ZP sheared prism. And so to specify such a map, I can specify a bit vector that satisfies some conditions. And so it classifies from the bit vector, which is the brackets Q analog of brackets P, but now I also have to rescale it by some unit. So brackets Q minus 1 over 2 times C. So there's a natural map like this. So there's such a map.
And where does this thing, this gadget, I'm a little bit, and square brackets means Techmuller
Yes.
element. And then there is some index. First of all,
Sorry, this is a power of brackets Q. This is brackets Q raised to the power minus P minus 1 over 2.
and then what is and then what do you what is the meaning of subscript square brackets?
Yeah, sorry. So this is brackets Q to the minus P minus 1 divided by 2. So this factor is just making a polynomial symmetric and Q inverse times brackets Q P minus 1 divided by brackets Q. So this is a bit vector.
Yes. And so this lives in right, it lives in W of what?
Here. And I guess the claim is that it defines a point of ZP sheared prism. So in fact, its difference from P is in W hat.
And if P equals 2, then
you got a square root
completely
of Q.
broken. No, and you are saying that this construction doesn't work, but in all other situations, it seemed at first glance you think that P equals 2 is an exception, but after it turns out that in fact it's not an exception. So is there some hope to get something similar for P equals 2?
I think if you have a square root of Q, then you could still do this. But, okay, maybe I should just try to wrap up. So this is the map. So this is a deformation of the de Rham point. And this point is related to the Q differential operators. So when Q equals 1, it becomes the de Rham or crestfallen point. It's greater than 2. The other thing to say is that Okay, so. All right, so, well, there's a map, so the Q line has a natural action of the group ZT cross in raising Q to a power. And in fact, this is going to extend over a map like this. So the point is that if you raise Q to a power, you will change this by a unit which is small. And inside here, you have both ZP mod ZP cross. You set Q equals 1, this becomes. Okay, so you get a diagram like this. So roughly speaking, what this is saying is the following. If you have a,
so how does ZP map to?
so this is the trivial action.
In the upper left corner, you have ZP of Q or ZP.
So it's both of ZP.
And then it contains, and then the left vertical arrow or inclusion corresponds to Q equals 1.
So, okay, so roughly speaking, what this is saying is that if you have a module on ZP shear prism, you can pull it back to the Q line, and pull it back here, and it has an action of the group ZP cross, such that this action becomes trivial when you set Q equals 1. And I guess the result is, which is an extension of result of Vadim-Lurie, essentially an application of a result of Vadim-Lurie, is that on quasi-co it's a pullback. So an object, so the conclusion is that quasi-co of ZP sheared prism is the pullback of the above diagram. So this is saying.
But we don't have to. If we don't understand why, then we have the right not to understand.
Okay. Yeah.
So this is a variant of a certain theorem of Bhatt and Lurie.
Okay. Anyway, I think I should end here, but I just wanted to say that I think in many of these cases, quasi-co of X sheared prism can be described in terms of some sort of relatively concrete construction, and that in this case it's just some modules with some endomorphisms with some.
Just Bhatt and Lurie proved this for ZP prism, but
Yes.
you claim that this is true for ZP sheared prism. Yes.
So
is it? Do you claim that it's true for?
So right. So the statement is that what Vadim-Lurie show is that an object on the ZP prism is determined by so Vadim-Lurie prove a full faithfulness statement. So basically, we're claiming that if you do the shared version, you get essential surject.
So just what? So Bhatt and Lurie worked with the non-shared version, and they have and they said that something is fully faithful.
Yeah.
And you are saying that in the shared version, it's an equivalence of also equivalence. Okay. So the statement to write down, but not, I have the right not to understand it, is that the theorem becomes even better in this shared version.
There is a head missing, right?
No, sorry, I was just saying. Oh,
Okay.
yeah, sorry. Here, there's a help. Okay, maybe I should stop here.
Some notes would help.
I'm writing some notes. I will share them.
I understand that as far as this lecture is concerned, it's possible to make them available right away, but at least something related to the, it would be nice if, probably there is no problem to make available the notes corresponding to your first lecture.
I'm writing some notes. I
And
will share them on-
eventually to this one also.
Thanks.
Are there questions or comments?